Looks like I'm not going to have a sub for tomorrow and Thursday. And so what was suggested earlier, I could post some mini lectures on YouTube. Would you guys watch those, or yeah? All right, that's what I'm going to do. I'll post some stuff over the weekend. You can take a look. Not too far behind. Yeah, sorry about that. I just couldn't get out of this. Anyway, we're talking about these species here. So we have another table. And this other table, we're looking at a different property. The property we're looking at is whether these species are electron poor or electron rich. And so all these species here are considered electron poor. And the most electron poor species would be F2, fluorine. Then it would go down. What makes fluorine electron poor? What makes it electron poor is it really wants just one electron. If we scroll down here, on the opposite end of this table, we have these metals here, like lithium, potassium, calcium. Metals are electron rich. So these species are the most electron rich. Lithium would be at the top of the list for electron rich species. So electron poor, electron rich. Now lithium is considered electron rich, so we have the conjugate relationship coming again. The conjugate relationship is just this. If fluorine is really electron poor, then it really wants electrons, so it takes those electrons. Once fluorine takes those electrons, it forms fluoride. Now, fluoride itself is stable. Fluoride, having gained that electron, is happy. And so fluoride is happy as is, although metathesis is pretty nasty. There's so much fluoride it has precipitation. Calcium. And so the conjugate relationship holds here, just as we saw for strong acids. It's conjugate, it's weak. So if this is really electron poor, its conjugate is happy as is, not electron. Okay, now let's take a look at some electron poor species. Fluorine is the most electron poor, and then what's this here? O3. Okay, so I made an announcement. There weren't that many people in class at this time, but as of yet, I still do not have a substitute. Somebody can come in, sub for me, tomorrow and Thursday. And so there's going to be a sign-up sheet probably on the door, but you could save yourself a trip if it's your only class. Don't bother to come in, otherwise nobody's going to be here. So what I'll try to do is I'll try to post something on YouTube, just a mini lecture. That's going to be chemical reactions. Now this stuff is not in the book. Not being in the book, I want to talk because we're about to hit chemical reactions, and we were talking about chemical formulas. So we're about to hit it. So here, when we look at F2, what makes it electron poor? Well, F2, what makes it electron poor is it's just one electron shy from being fluoride. It wants to be fluoride. And so, how do you know, or why? Well, you just kind of memorize it. This is what's observed. That means, what do you think about chlorine? Is chlorine electron poor too, or? Chlorine's electron poor too, but not as electron poor. In fact, chlorine's here. A bit weaker than fluorine. Why would you think chlorine would be a bit weaker? One of the reasons that chlorine's a bit weaker is it's a bigger atom. You know, chlorine's a smaller atom. Usually the small atoms are quite reactive. So we have fluorine, we have chlorine. What's after chlorine? We have bromine. So let's see, what do you think about bromine? Well, bromine's a little bigger atom still. And it's down here. Do you see bromine? Yeah, and after bromine is iodine. And there's iodine there. So you see the whole series. And so, you know, even though this chart is overwhelming, most people look at this chart and they're totally overwhelmed by it. There's certain patterns in there: fluorine, chlorine, bromine, iodine, that makes sense. Being the most electron poor species would be fluorine. Now, the next is, you know, ozone. Ozone. Have you ever breathed in ozone? Have you ever breathed in fluorine? It's a good thing you haven't, because it can cause some serious damage. But you might have breathed in some ozone, you know, from some electronic short or something, you know, some electronic fire, or pollution. You know, when there's a lot of smog, photochemical smog, there's a lot of ozone in the air. And ozone is going to cause a lot of irritation, a lot of burning in your eyes. Why? Because ozone's a pretty reactive chemical. Ozone is electron poor. It wants electrons. Where can it take electrons? It can take electrons from your eyes, or from your skin, or your mucous membranes, that kind of thing. Cause damage. But we go from ozone and then we go here. This seems bizarre because this has a -2 charge. If it has a -2 charge, it has 2 extra electrons. So why the heck would it want more electrons? And so why is this species electron poor when it has a negative charge? We'll have to think about that. Well, we'll go on down the list. So we got ozone, and then this one you should be able to recognize it. What's this called? Don't name it as the acid. You could name it as the acid if you want, but name it first as the ionic compound, and then name it as the acid. It's hydrogen peroxide is the name of the ionic compound. The name of the acid is hydrogen peroxide, IDE. Yes, right. So it'd be hydroperoxic acid. Hydroperoxic acid. It's like hydrogen chloride, you know, hydrochloric acid. This hydrogen peroxide is electron poor. It's a pretty good oxidizer. Hydrogen peroxide can be very dangerous. You know, household hydrogen peroxide is very low concentration, but if you buy commercial hydrogen peroxide, it's very dangerous. In fact, commercial hydrogen peroxide is used in gardening. Gardeners used it for soil. And so this was pre, you know, TSA days, but this was back, I don't know, a few decades ago. There's a story about somebody carrying some 50% hydrogen peroxide in a milk jug, kind of bottle, and then wrapped it in one of those Coleman type coolers, you know, those ice chests. This is plastic. Convinced the this would never happen now, but convinced the check-in person at the airline counter to check it as checked luggage. And so they took it and they put it inside the cargo container of the plane, and the hydrogen peroxide ate through the plastic jug and then ate through the Coleman ice chest, and then hit some fabric suitcases and caught those on fire, basically. And so fire broke out in the luggage compartment. They had to do an emergency landing. But, that's 50% hydrogen peroxide. Your household hydrogen peroxide is going to do that, but, it's a powerful oxidizer. Now, when something's electron poor, we call it an oxidizer. And so the most powerful oxidizer is fluorine on this chart. It really wants electrons, followed by ozone, followed by this. But oxidizers are electron poor species. They want electrons, so this is a little weird. And then this is a little weird too. What is this? Permanganate ion. Permanganate ion is an extra electron. Why is this electron poor? Then we go down here. What is this? Lead-4 oxide. This is lead-4 oxide. Lead-4 oxide, it turns out to be a more powerful oxidizer than chlorine. Chlorine, you might have smelled chlorine before, have you? It's pretty bad. This one, what would you name this one here? S208. Looks like it's two sulfates put together, right? But it's not like, remember when we put two chromates together, we dropped the oxygen? Yeah. So it came out Cr2O7. Shouldn't it come out, S2O7, and then we'll have two sulfates we can link together? Yeah, this could have a double oxygen, which is a peroxide link, making it quite unstable. If it's connected like that. Take a look at what we form here. Two sulfates. So this is most likely a peroxide link. Those peroxide links are on hand. Here we see another one. On and on. You should recognize this. What's this called? All right, so let's take a look. What we're going to do is this, before, it's not like, okay, all of a sudden you have to have this mastered, right? That's not how science works. A lot of people think that if they don't understand something the first time, then something's wrong. No, usually people, what they do is they go over it and over it and over it, and finally it clicks. Usually things don't click so quickly. The same thing here with a chart like this is difficult. So what we just do is we just observe, So fluorine, what happens is it takes two electrons. Each fluorine wants one, so we can end up with two fluorides rather than the diatomic fluorine. So this dissociates, and then each fluorine atom picks up an electron. And then ozone here, ozone picks up some, what's this? Hydrogen ions, some protons, and some electrons. So why do we need that hydrogen ion there? Why we need that hydrogen ion there is, take a look at what's the product. Do you see the product? Water. The hydrogen ions end up as water. Is water a very powerful reactive chemical? It's pretty stable, so it's good for water. Here we're going from this to this. I guess this would be like disulfate, maybe, like dichromate, but a little different. Then we have hydrogen peroxide. Hydrogen peroxide is picking up H plus and electrons to form water. And then we have permanganate picking up 8 H pluses. Look, how many oxygens are in permanganate? 4 oxygens. How many H pluses? 8. How many waters? 4 waters. If I have 4 waters, how many H's do I have? 8. And how many O's? 4. And so do you see a pattern there? No. A little, yeah. It's balancing waters. Let's see if we can predict this. PbO2 has 2 oxygens. How many H pluses do you think it's going to be? 4 to form 2 waters. And so it's going to pick up 2 electrons in the process. Here we don't need any H pluses. Here there's no oxygen. But do you see when there's oxygen present, it seems to like to form, except in this case it doesn't. So these are the types of things you notice, by looking at it and just reading through it. Not once, but many times. I've looked at this chart many, many times and tried to analyze it. Some people said, or asked me, do I need to memorize it? No, you don't need to memorize it, but then again, you shouldn't ignore it, A lot of people say, oh, good, I don't have to memorize it. I'm never going to look at it again because I can always look at the chart. But the problem is yeah, you can always look at the chart, but is everything in life going to be on this chart? Everything you encounter? No. There's going to be plenty of stuff you encounter that's not going to be on the chart. Now, how are you going to figure it out? The only way you're going to figure out something that doesn't occur on the chart is by knowing some patterns, and then being able to relate it to other things. One of the biggest complaints, like at UC and UCSB, UCLA, a lot of students will complain that the test is nothing like the homework, or nothing like this or nothing like that. But it is if they saw the patterns, then they could, it's exactly like it. It's just it wasn't the exact same thing. It's just following the same kind of trend, kind of thing. And so that's an ongoing thing. And so once you know to that level, then you can do those problems that give students a hard time. A lot of students a hard time. But anyway, let's continue here. This is picking up 2 electrons. You go to 2 chlorides. This is dichromate. It has 7 oxygens, picking up how many? 14 and 6 electrons. And it's going to form chromium-3 in water. What did we call dichromate? We called it not chromium-3. We called it chromium. It's that Aaron Brockovich thing. I forgot earlier. Chromium-6, yeah. Where did that chromium-6, where did that, I see 272, I don't see 6. Where did that 6 come from? We're going to analyze this one a little bit more because we talked about chromium-6. And so the way we're going to analyze this, okay, we have dichromate here, Cr2O7 2-. And how did we figure out it was 6? We figured out it was 6 because we have 7 oxides. Each oxide is 1, 2, 3, 4, 5, 6. Each oxide has a charge of 2-, right? And then we had 2 chromiums. Each chromium it's got to be +6 because I'm going to get +12 minus 14. This got to equal -2 net charge on this. I got to have 2 extra electrons, which I do. Imbalance there. But this is chromium +6. Now, what do we know about chromium +6? What do you know about chromium +6 on the periodic table? Can it go to chromium +7? No, that's it. That's the max. Is it happy? If somebody lost 6 of its electrons, would you be happy if you lost 6 of your electrons? No, it's unhappy. Chromium's unhappy. Chromium 3+ is a lot happier, a lot more stable than chromium 6. This is a free, what we call a free ion, or it's just chromium. That's it. When I look at the chromium 6, I use a Roman numeral for this because it's not a free ion. In order to get chromium in the +6, we have to have it with oxygen. And therefore, it's not alone, standalone, chromium 6+. It's chromium 6 within dichromate. And so we always use Roman numerals in that case versus a regular charge. Yes. Okay, so what's going to happen is this. Then I have 14H plus. 14H plus, and then plus 6 electrons. I'm going to do a 3 electrons plus 3 electrons. I'm going to split it out like this. So that gives us a total of 6 electrons. This is going to go to 2 chromium 3 pluses. So I've got a chromium 3 plus here and a chromium 3 plus here, and then 7 H2Os. If I do 7 H2Os, I'm going to write it like this. So here I'm going to go with 14 H pluses. Actually, maybe I should write them out. Sorry, I'm going to write them out. H plus, H plus, H plus, H plus, H plus, H plus. 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 H pluses plus 6 electrons, which I'm going to break up into 2 groups here. This is going to go to 2 chromium 3 plus 7 H2Os. Yes. Now, the H2Os, we'll see what happens. Can you see what happens now? What happened? What happened is that that the chromium 6, each chromium 6 must have picked up how many electrons? 3 electrons. So this chromium 6 takes these 3 electrons here. This chromium 6 takes these 3 electrons. This chromium 6 is not so happy. It wants electrons. What do we call oxidizers? We call oxidizers electron poor. Chromium 6 is electron poor. It wants to take electrons. And so it's going to take electrons. When it takes electrons, we end up with chromium 3 now, because now we've got 3 electrons. We can reduce the positive charge by 3. And then the waters. The waters are going to come about. For each O2 minus, we need 2 H pluses. So we'll form H2O. When we look at the waters, did anything happen? Because if I look at waters, I'll have 2 H pluses in the O2 minus, as far as thinking in terms of ions. And so basically nothing happens here, because did the oxide pick up any extra electrons or lose electrons? No. Because we have oxide, O2 minus on the left, we have O2 minus on the right. Did the hydrogens, did anything change with the hydrogens? No. The only thing that changed was the chromium. And so it was the chromium in dichromate that took the electrons. Does this make sense? Somewhat? Yes. Okay, so even though that dichromate has a -2 charge, we still consider this very electron poor. Why do we consider this electron poor? Because of the chromiums. Not because of the oxides. Oxide is very happy. Is water very reactive? No, water's stable. And so oxygen is very happy with 2 electrons. It doesn't want to react. So this is stable. And hydrogen's okay with a plus here. And so these are what we call stable charges. These charges we give a different name to. When we do charges like this, like I'm doing on the board here, we call them oxidation states rather than charges. But essentially they're just the charges. And so what we say is the oxidation state of chromium in dichromate is +6. The oxidation state of oxygen in dichromate is -2. The oxidation state of hydrogen in hydrogen ion is +1. These are just electrons here. The oxidation state of chromium 3 is 3+, and the oxidation state of hydrogen in water is +1, and the oxidation state of oxygen in water is -2. And we see the oxidation states change for the chromium, but they didn't change for anything else.
this equation, there's 14 H pluses, meaning that there's 14 hydrogen that have lost an electron or are willing to take one, and then there are only 6 electrons that are being added.
Yeah.
Are those related at all? Or
No.
those just
Those are not connected at all. The 14 hydrogen ions, nothing happens. They don't pick any electrons up. And so when we go from the left here, we have a hydrogen ion, the H plus. It has a +1 oxidation state. Well, in water, hydrogen has the same charge, +1. It just comes together and bonds to form a stable molecule. It's a little bit more complicated than that. But the only reason that we think in this way is if we put in all the variables in here, it becomes horrendously difficult. Yeah, and so we just try to simplify things. I mean, water is not exactly the same as H plus. You know, H plus is much more acidic. In fact, we call H plus, we call that hydronium. We consider a strong acid. And so it's a little bit more to it than what I'm talking about. But this, even though there's more to it, this is the way people think about it, and this is the way people use it. We got to make it into something that's easy to use and easy to make predictions. And so, even though I'm oversimplifying it, I just realized, yes, I'm oversimplifying it, but I'm not going to work any harder. This is it. Let's do our analysis. Well, now there are some simple rules for figuring out the oxidation states on the elements. And the rules go like this. Actually, let's look. Let me show you. We have a set of rules in our Chem 4 supplement. And there's a whole page of oxidation state problem. But rather than doing that, I'm just going to, just thought of doing this, yeah. I'm going to go to, the Chem 4 rules and the Chem 1A rules are no different. Well, I shouldn't say. They're a little bit different, but essentially just very minor. So let's familiarize ourselves with this rather than the Chem 4. That way you don't have to redo it. But once you have enough practice, you don't even need a set of rules. It's pretty straightforward. You know, we've already been doing it. I mean, you've already predicted this. For example, permanganate. Can you tell me the charge on manganese, permanganate? It's MnO4 minus. MnO4 minus is permanganate. What's the charge on manganese? charge on manganese and permanganate?
Oh, it's 7.
Oh, 7. Did everybody get it? No, I meant, yeah. Yeah, it's +7 because the oxygen is -2. How many oxygens do we have? 4 of them. And so we have the total negative charge will be -8. So the total positive charge must be +7 in order to give an imbalance to the charge, which is -1. So this is +7. Is that clear? So what you just did there, how would you express that as a rule? You know, how would you write that down in like a verbal rule? Well, this is how you'd write it down in a verbal rule, and this is it. So the rules for assigning these charges, which we call oxidation states. So oxidation state is the charge on an atom. Parent charge on an atom. I should say the parent charge on an atom. So the oxidation state, this is abbreviated OS, of an individual atom in a 3-element uncombined with other elements is 0. So for example, what is the oxidation state of a helium atom? There's no charge on it. Well, if you have a helium atom with no charge in the oxidation state, the charge is 0. What is the charge in Cl2? What's the charge on each chlorine atom in Cl2? I have 2 chlorine atoms there. Okay, if this one's -1 and this one's -1, then the whole thing is -2. Is the chlorine Cl2 2 minus? No, it's not. It's just Cl2, no charge. And so how can we get this to be no charge? Well, each atom must be not -1. Each atom must be neutral. Each atom must be 0. And so we have this rule. I rewrite this. The elements in elemental form have an oxidation state of 0. That's my rule 1. Elements in elemental form have an oxidation state of 0. No charge. Okay, let's move on to number 2. Number 2 is how we figured out the charge on manganese. How did we figure out the charge on manganese? Well, we figured it out by 2B. But let's look at 2. The sum of the oxidation states of all the atoms must equal the net charge. I simplify this. I just say the sum of the oxidation states of all the atoms must equal the net charge. But Cherty, the author of this book, breaks it up into 2. He says the sum of the oxidation states equals 0 if there's no charge. But if there's a charge, then it equals that charge. So this is too much for me, so I just say the sum of the oxidation states is equal to the net charge. Of course, the net charge can be 0. It doesn't have to have a charge. This is what we just did with chlorine. The sum of the oxidation states is equal to the net charge. The net charge is 0. So what are the oxidation? The oxidation states got to be 0 too. So we've already done number 2. That's how we figured out chromium as well. So this is just putting down, you know, kind of what we're doing into words, except it's a little bit more breadth to it because there's more stuff here. In their compounds, the group 1 metals have an oxidation state of +1. Well, you know, what is the charge of group 1 cations? +1. There you go. The charge on a group 1 cation is +1. So for example, potassium carbonate, what is the charge on potassium? +1. What about group 2? What is the charge on group 2? +2. So magnesium bromide has a +2 charge. Same thing with magnesium nitrate. Okay, now you're going, well, you know, do you really need to say that? Yeah, the reason is there's an order to this. The order goes like this because of there are some atoms that have multiple oxidation states, like iron. Iron can be +2 or +3. And so we need a little sequence to this. We can't just say iron is +2, right? Sometimes it's +3. And so by going along this order, we can figure out, is it iron 2 or is it iron 3? Because we can easily figure out if it's iron 2 or iron 3 by looking at the anion first. And so here, we got to go in this order. Otherwise, you know what might screw us up? What might screw us up is peroxide. Peroxide could always screw us up. And so this is why we have to go in the sequence 1, 2, 3. Otherwise, we might get peroxide wrong. But if we go in this order, we'll get peroxide correct. All right, in its compounds, okay, so basically this is the way I remember it. Okay, when I'm thinking about oxidation, I look at the charge. If it's group 1 or group 2, do those first. And then go to fluoride. You know, fluorine wants that electron the most, right? To form fluoride. And so the oxidation or the charge on fluorine is always -1. Okay, so what I do is this. Group 1, group 2, and then I think what wants the electrons the most. What wants the electrons the most will get them. And so if not fluorine, let's say we don't have fluorine, then maybe oxygen. Oxygen really wants electrons. Chlorine really wants electrons. Those species really want electrons. And so, here. And then hydrogen. Hydrogen, you know what? I don't even put hydrogen here. I put hydrogen in group 1. And so I eliminate this step, and I consider hydrogen as group 1. Unless I have another group 1 in there. And then it could be a hydride, like an anion. So if you follow this sequence. In this compound, oxygen is usually -2. In compounds, nitrogen is usually -3. And so this just says the oxygen family is -2. And so in other words, we're going down the periodic table. +1, +2, +3, -1, -2, -3. Standard charges. That sequence is just because sometimes we have variable charges, and that's it. And so, you know, I don't have these rules memorized, and I don't really use these rules. You know, I just figure it out. So the more practice you get figuring it out, the easier these become. And so let's get some practice figuring these out without even referring to the rules. Analyze some of these, what we call redox. All right, oxidation state. Each fluorine atom has what charge? 0. Good. It's an element. 0. Oxidation state. It's -1. It's pretty obvious. Each fluorine's got a -1 charge. Ozone. Ozone's also 0. It's, even though it's not the most common. What's the most common form of oxygen? O2. But still, this has got to be 0. I mean, sometimes people put -2 because oxygen loves -2. But if you have 3 oxygens put together, how can each of these be -2? Because that would give you 6 ion, and it's neutral, so it's not minus 2. Anyway, that's ozone. The oxidation state of hydrogen, +1. And then we go over here. Oxygen, 0. And hydrogen is +1. Oxygen is -2. And so usually the sequence goes do hydrogen first and then oxygen, because oxygen can have variable charge. What are the variable charges on oxygen? Well, it could have 0, it's 1. It could have -2, which is by far the most common, but it could also have -1. And there's one more it could have, that's -1/2. -1/2 in superoxide. But anyway, that's more rare. Well, actually, it's not so rare because superoxides occur in the body. Well, anyway, so what happened? Well, one of these oxygens out of 3 went from 0 to -2. So one of the oxygens out of 3 gained how many electrons? 2. So here's the 2 electrons it gained, and it went from 0 to -2 over here. And we have oxygen. Oxygen itself can gain 2, as we'll see down here. All right, now we're going to follow the rules for this one, but this one, the bonding is a little tricky. So this is definitely a tricky one, but let's take a look at this. Which one would we do first, sulfur or oxygen? Well, it depends which one wants the electrons more, sulfur or oxygen. I would say oxygen wants them more. Oxygen's smaller, right? Wants the electrons more than sulfur. In other words, oxygen is a more powerful oxidizer than sulfur is, for sure. All right, so that means oxygen is -2. And so that's -16. -16 plus 14 would give us -2. So we're using rule number 2. And so if we have +14 net positive charge, that means each sulfur must be +7. But you know, a sulfur at a +7 is very weird. Why is that? The sulfur at +7 is extremely weird because, let's look at the periodic table. Tell me what's weird about sulfur at +7. I wouldn't expect it. You know, what would the highest positive charge be expected for sulfur? +6. I would expect sulfur to be +6. Not if it's +7. That's to fluorine. Fluorine's not happy at all. So, you know why? Because we made the wrong assumption. We assumed that every single oxygen is -2. And that. I made the wrong assumption. I was thinking every single oxygen is -2. It's not. One of those oxygens, remember dichromate? Well, we have this scenario here in this. This is disulfate, but it's 2 sulfates linked together like this. And so sulfate is like this. It has 4 oxygens attached to the sulfur. And if I have another sulfur here, what I should do is I should lose one of those oxygens, because oxygen-oxygen links are not good. But in this case, it doesn't. And so what we end up with is an oxygen-oxygen link. An oxygen-oxygen link is called a peroxide. And a peroxide link, do you know what the charge on oxygen is in a peroxide link? -1. -1 is not happy for oxygen. It's kind of unhappy. And so if these were, okay, now this changes things, because now I have 3 at -2. So -2, -2, -2, and then 1 at -1. That kind of thing. And so in that case, it brings a charge. about in line, but the peroxide link is not so great. So you can see right below it is hydrogen peroxide. And so this one is a bit more advanced, so I'm not going to say much more about that. But hydrogen peroxide we should be able to figure out quite easily. So what do we do? Do we do oxygen first or hydrogen first? We do hydrogen first. We have to do hydrogen first because think about if we did oxygen first. If we did oxygen first, we got 2 at -2. 2 at -2 is -4. We got to have +4, which means each hydrogen must be +2. But how many electrons does hydrogen? Hydrogen only has 1 electron. How can it lose 2 electrons? It's impossible. So it's impossible for hydrogen to have plus. So the only reason I worry about the sequence is because of peroxides and maybe hydrides. Hydrides, hydrogen -1. But anyway, if we do hydrogen first at +1, that means oxygen is -1. That's what we expect with peroxide. This is +1. Over here, hydrogen is +1 and oxygen is -2. So that means each oxygen gains 1 electron. Well, we have two oxygens. Each oxygen gains 1 electron. We're going to end up with water there. Let's see what happens with permanganate now. Looking at permanganate, which one do you do first? Manganese or oxygen? We got to do oxygen first. Manganese is variable charge. We don't know what it is. And so this is, the 2 most common charges for manganese are +3 and +2. But it could have higher charges. Those are for free ions. It could have higher charges when it's bonded like this. But each oxygen is -2. That means manganese is +7, like you guys figured out. Now what happened here? We're going from +7 all the way to +2. How do we go from +7 to +2? We must gain 5 electrons. So we gain 5 electrons. Now what happened to the H+? Nothing happened to the H+. But if nothing happened to the H+, why do we need it? Well, nothing happened in the sense of charge because it went from +1 to +1. But something happened in the sense of forming some stable compound, water. And so we need the H+ to form the stable compound, water, that helps the reaction go. Here we're going from lead. Well, which one do we do first, oxygen or lead? Oxygen -2. -2 is -4. That means this is going to be +4. So we're going from lead 4 to lead 2 by gaining 2 electrons. Now, we're going from this with oxygen, so we need to get rid of the oxygens by adding acid. This is called acid, H+. Here, going from chlorine 0 to chlorine -1, we got 2 chlorines, so we need 2 electrons. Here we have our dichromate. Going from chromium 6 to chromium 3, we already talked about that. What's this called? MnO2. Geologists often call this manganese dioxide. They call it manganese dioxide, which is okay, but technically it should be called manganese, not manganese 2. Which one? Manganese or oxygen goes first? Oxygen goes first at -2. Therefore, manganese must be +4. This would be called manganese 4 oxide. Manganese Roman numeral 4 oxide, or manganese dioxide, or there's another name for this mineral. It's called desert varnish. Desert varnish forms a black coating on some sandstone out in the desert. Really tough. But anyway, it's going from manganese 4 all the way to manganese 2 by picking up 2 electrons. We're getting rid of the oxygens by forming water with acid. What's this What's the charge on oxygen? 0 each oxygen atom. So it's going from there to, what's this? Water, oxygen, well, hydrogen we go first at +1. Oxygen would be -2. And so how many oxygens we have? We got 2 oxygens. Each oxygen is going from 0 to -2. So each oxygen needs how many electrons? 2. Therefore, we're going to need 4 because we got 2 oxygens. And then we have throw in some acid there to form water. You should know the name of this one. Iodate. All right, let's analyze the charges. We do oxygen first at -2. It's -6. That means this has got to be +5. So we're going from iodine +5 to iodine 0. And so iodine +5 to iodine 0 means that iodine must gain 5 electrons. But 10 electrons are gained here. Why? Because there's 2 iodines. Again, we throw in some acid there to bond to the oxygen. This is elemental bromine. 0 charge, bromide, so each one picks up 1 electron. This is the sand. Nitrate. This can't come out yet, that's smart. This is nitrate. What are the charges? Oxygen's -2, nitrogen is +5. So we're going from nitrogen +5. Oxygen, nothing happens because this is -2, that's -2. Nothing happens with oxygen. But the nitrogen does, something does happen. If this oxygen is -2, that means this nitrogen is +2. So we went from nitrogen +5 to nitrogen +2 by gaining 3 electrons. And again, the acid, oxygen. Okay, silver ions. Silver ions are pretty decent at picking up electrons too. Silver ions are relatively electron poor. You got to watch out for silver salts. Silver salts containing silver ions love to oxidize things, especially your skin. We were doing an experiment with silver nitrate, and the student accidentally spilled silver nitrate on their hands. And she came up to me during the lab. I had mentioned this earlier too, but she came up to me during the lab, actually at the end of the lab, and she said, "I've been washing my hands for 20 minutes. The black stains aren't coming off my hands. I have an important job interview right after class." She's got all these silver stains. And the black stains are silver metal. You know, little tiny crystals of silver metal deposited there after oxidizing her skin. And those don't wash off because so eventually it will come out. But it was quite a shock. Eventually it'll come out. Not for a week or two though. Yeah, so it was a very awkward interview. Iron, what's this on? Iron 3 is going to iron 2. So +3 to +2 by gaining. This is oxygen again. Why didn't we just do oxygen? Things you notice. You might not notice or even care. You know, a lot of people don't care until they have to use it, and then all these confusing things come out. We just did oxygen in H+. What's the difference between this oxygen and this oxygen? This one's 2 hydrogen, this is 4 hydrogen. This one forms water, this one forms hydrogen peroxide. Which one's more stable, hydrogen peroxide or water? Water. And so which one's better? This one's better. If this one's better, then why have this one? Why have this one is because this is a dual purpose table. This table, we don't always go left to right. This table, we can go the opposite way. And so we don't have to have 2 tables written if we can just make one table that does 2 things. And the one table that does 2 things, we already saw this. That was the acid-base table, in which we had the acids on one side and the bases on the other side. This table does the same thing. We have the oxidizers on one side, or the oxidizing agents on one side, and on the other side we have the opposite of the oxidizing agent. The opposite of an oxidizer is a reducer. And so having 2 oxygens here is not to confuse you, meant to confuse you. You pick this one. This is the better one, the stronger one. Right? This is the reason for 2 oxygens is because they're looking at the reducers. We can have hydrogen peroxide as a reducer, which forms oxygen, or we could have water as a reducer, which also forms oxygen. Turns out hydrogen peroxide is a better reducer than water. And so this one forms hydrogen peroxide instead of water. Okay, below oxygen is iodine. Iodine is normally a solid, purple crystals. Bromine is normally a liquid. Chlorine is normally a gas, and fluorine is normally a gas. So we can see iodine. If you look up here, bromine is an L rather than an S for liquid. This is picking up electrons. We know that that's what they want to do. Okay, what is this? Copper 2, picking up 2 electrons to form copper. What do we call that? Copper metal. What's the charge on copper metal? 0, neutral. There's no charge on copper metal. Okay, then we have this sulfate. Let's look at the charges. Oxygen is -2, sulfur is +6. So this makes sense. Remember the sulfur we saw earlier was +7. That didn't make sense because +6 should be its max positive charge. So this one makes sense. It can have lower than its max, like sulfite, but there's no sulfate in this case because that would exceed its max. The 8s don't always refer to the max. You know, the 8s are just historical. They have a historical context to them. And so this is sulfur going from +6 to sulfur. What's the sulfur over here? +4. So it goes from +6 to +4 by gaining 2 electrons. We have information water. This is, what's this one called? Tin 4 going to tin 2, 2 electrons. This is sulfur, elemental sulfur, picking up some H plus to go to we would call this hydrogen sulfide gas. Normally it's a gas. If it were aqueous, we might call it hydrosulfuric acid. Then we have H plus. You know H plus is an oxidizer too. So H plus can react with bases. When it reacts with bases, it's not transferring electrons. But it can react with metals as well, picking up electrons from metals. Hydrogen gas. Then we have a whole bunch of metal ions. Lead 2, tin 2, iron 2, zinc 2, aluminum 3, magnesium 2, sodium plus, calcium, potassium, lithium. Now, here's where the conjugate really come into play. Which one is more stable, sodium ion or sodium metal, do you think? Yeah, so for example, if you want to decrease the amount of sodium in your diet, if you decrease the amount of sodium in your diet, are you decreasing the amount of sodium ion intake or sodium metal intake? Sodium ion intake. You shouldn't eat sodium metal. Do you know what would happen if you ate sodium metal? Let's take a look and then we'll go off right. There's a video, there used to be a better video. It was just the original without this commentary. But let me just show it to you. Here. It's surplus sodium disposal. 1947. I don't know if this one was the one with the commentary. Let's take a look at this. This is sodium metal here, not sodium ion.
Government surplus chemical ignites and explodes when wet.
Okay. Sorry.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assist Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Is that bad for the environment?
Yeah. Well, they said it's an alkali lake.